So what we're going to do is we're going to look at the relationship between the temperature of a reaction, its rate law constant, and its activation energy. Now, one of the things we know is that when we change the temperature of a reaction, the rate at which it occurs also changes. But the order of the reaction in terms of my reactants does not. What does change, though, is the rate law constant, or K. And so there's a relationship between the rate law constant and my temperature. Now, this relationship was described by Arrhenius, and what he said was that my rate law constant K is equal to some frequency factor A times e to the negative EA, which is my activation energy, over R, my rate law constant, times the temperature. Now my temperature has to be in Kelvin, and my ideal gas law constant has different units, but it's still the same value. One of the things that this equation shows us is that fraction of molecules with sufficient energy for an effective collision. Now, we can take this equation and we can take the ln of both sides and manipulate it, and it helps to get rid of the e, and puts it in a form that's of much more use, where ln of k is equal to ln of a minus EA, my activation energy, divided by R over T. Now this format is much more useful because we can see a couple of things. The greater the activation energy, the smaller my rate law constant. The other thing we can see is that my change in temperature will have drastic impact on my rate law constant because my activation energy is divided by my temperature. So, how does this help us? Well, the derivation of this formula can be used to determine my activation energy in one of two ways. The first way is I could graph my ln of k versus 1 over temperature. The other way is if I had the rate law constant and the temperature for two different trials, I could determine my activation energy. And we're going to look at both of them. So let's take a look at the graphical method first. And what we find is if I take my ln of k is equal to ln of a minus EA over RT, this equation has a familiar format that we've seen before already in this unit, because it takes the format of y is equal to mx plus b, where in this case b is my ln of a, my x will be the inverse of temperature, 1 over t, which means that my slope for this graph will be negative EA over R. And so if I were to plot one of these graphs, I would see that I have my ln of k on my y-axis, my inverse of temperature on my x-axis, my intercept would be the ln of a, and I have my slope, which gives me my activation energy divided by my rate law constant. So let's take a look at an example. Now in this example, we're going to look at the decomposition of nitrogen, and this experiment was conducted at 5 temperatures, and we have the rate law constant for each of them. So now, in this case, it was done similar to how we did our lab, where they conducted a number of trials at each temperature, plotted the graph to determine the slope of each of the graphs, and got the rate law constant from each of them, and they knew the temperature at which the system was occurring, which allowed them to determine will allow them to determine their activation energy. So for our graph, the first thing we have to do is we have to take the ln of k and the inverse of temperature. So we take those, and we have our values. And now that I have my values, I can plot my graph, where ln of k will go on the y-axis, inverse of temperature on the x. And so I plot my graph, and I have my points, and I add my line of best fit, and then I can determine the slope. And so now with my equation, I can see my ln of k, my y, is equal to ln of a, which would be my intercept, plus negative EA over R times 1 over t. And so here I see that my slope is negative 13,605. Since my slope is equal to that, and my rate law constant is 8.314 joules per mole Kelvin, I can use the relationship that slope is equal to negative EA over R to solve for my activation energy. So I can manipulate the equation and isolate for my activation energy and substitute in my values, and I see for this reaction that my rate law constant or my activation energy is 1.2 times 10 to the 2 kilojoules per mole. Now, our second method for determining our activation energy is a two-point method, where I would take one trial and subtract it from the other. And in doing this, I end up with this derivation of the equation. Now, the key to understanding this is, regardless of what trial you call what, when you're substituting in the equation, the higher temperature is always T2. So therefore, the rate law constant that goes for the higher temperature is always K2. Okay, so we're going to look at an example where we look at the decomposition of my hydrogen monoiodide. I'm going to summarize my values in a table. Then I have my equation. So now I substitute them into my equation. And now it's just a matter of solving. So we solve the equation as we go along, calculating some of the different parts first. And then finally, we isolate for our activation energy. In this case, we get our activation energy is equal to 1.8 times 10 to the 2 kilojoules per mole.